frequency response. What's that? Why do we need it? What's good? What's bad? That's what I'm going to talk about today. Hi there, this is Marius Loubeeka from Hamburg, Germany. And today I have a new concept, the Loubeeka podcast. I'm going to produce it now frequently, and I'm going to discuss some topics of loudspeakers in general and some basics about loudspeaker technology. And today we have the first episode with the topic frequency response. I also produced this in German, and therefore I'm not planning on creating subtitles for the German version. Normally, if you talk about frequency response, you mean the amplitude frequency response. There's also the impedance frequency response, but normally if you talk about frequency response, you mean the amplitude frequency response. Okay, amplitude frequency response. What's that? In the plot of the amplitude frequency response is depicted how loud the speaker or whatever you measure is at every single frequency. I just remembered and forgot to tell, in German version is it's called also Bode diagram. Usually you have a dual logarithmic diagram. Both axes are logarithmic. The frequency axis is logarithmic, which means that distances between the frequencies get smaller the further you go to the right of the diagram. For example, each decade has the same width. So the decade from 10 to 100 Hertz is exactly as wide as the decade from 100 to 1000 Hertz. And also the y-axis is logarithmic, the volume, but that is due to the fact that it's measured in decibels, and decibel itself is a logarithmic unit. The reason for the logarithmic scales is that your hearing works logarithmic, and also the volume contraception is logarithmic. For example, if the volume of something is doubled, then this means the value for the sound pressure level is 10 decibels more. Usually the frequency response is measured in a distance of 1 meter. And with the power of 1 watt on the loudspeaker, which is only the case for 8 ohms. Usually amplifiers work as a voltage source, and therefore you adjust the voltage to 2.83 volts, and that is exactly 1 watt at 8 ohms and 2 watts at 4 ohms, for example. Usually you plot the frequency response in that range where the hearing of a human is. So that means from about 16 or 20 Hertz to 20 kilohertz. The highest audible frequency depends on your age. If you're older, the highest frequency you can hear is lower than if you're a small child. I, for example, can only hear to about 16 or 17 kilohertz. To be precise, it's not your ears that get worse over time. It's the brain that just doesn't compute these frequencies anymore in your consciousness. In your subconsciousness, these frequencies are still processed. I think it's up to 100 kilohertz that you are able to hear, but, well, not processed in your consciousness. So that is also one reason why modern digital sound formats like on DVD, like Dolby Digital or like DTS, are recorded with a sampling rate of 96 kilohertz. That gives an upper cutoff frequency at 48 kilohertz. And the other reason that's done is you usually say that from 7 kilohertz on a CD with 44.1 kilohertz sampling rate, the quantization of the sound is not precise anymore. So you shift this upper frequency of true quantization to a higher range. My favorite loudspeaker DIY magazine, Hobby HiFi, also measures frequency responses up to 40 kilohertz. That is also due to the fact that in the last 20 to 30 years, let's say, the tweeters have gotten better. The upper cutoff frequency of tweeters has gone far up. Modern tweeters like the Beryllium tweeters from CS, ScanSpeak or SB Acoustics have a upper cutoff frequency at over 40 kHz, and even bigger dome tweeters with 30 millimeters diameter still have upper cutoff frequencies at 20 kHz nowadays. Your hearing has the highest sensitivity between 2 and 5 kHz. A still very high sensitivity is between 500 Hz and 6 kHz, and generally the hearing is quite sensitive between 200 Hz and 10 kHz in general. That's the range where a speaker should have its most linear and balanced frequency response. More on that in a minute. What's the frequency range of music? Usually it starts at 40 Hz. That's where most instruments have their lowest note. 40 Hz is about the frequency of the low E of a double bass or an electric bass guitar, which is the E of the contra octave. So that is sufficient for most songs. Of course, there are instruments that can produce deeper notes, such as organs or some pianos, as for example the Bösendorfer Imperial Grand, which reach the lowest C of the subcontra octave, 16.4 Hz. I once heard about organs that can even reach one octave below that, but those notes are more likely to be felt with your body than heard with your ears. Below 16 Hz, human perception is fast enough to recognize that as individual events instead of a continuous tone. I saw an interesting YouTube video about that the other day. I believe it was called "What's the Slowest Music Possible?", but I forgot by whom it was. But of course you can search for it if you like. Generally, the frequency response is divided into the ranges bass, mids and treble. I'd roughly put the border between them at about 400 to 500 Hz and 2 kHz. You can of course specify more detailed ranges. Hobby HiFi uses, for example, fundamental range, by which they mean 200 to 400 Hz, I think, but I don't want to be too exact with those ranges. I didn't bother to remember because I don't use them in everyday life. So these frequencies I mention are only rough values, where I'm not sure if I remember them correctly. There's presence about 5 kHz and brilliance beyond 10 kHz, and for the further ranges I can't remember at the moment. But as I said, I don't consider it important to know where is which range. Otherwise you would know by now. What else is important in acoustics? It's important to know that something exists that is called room modes. These are resonances of the room in which you listen to music. They are present up to about 100 Hz. Beyond that, the acoustics of your room is not that much influenced by that phenomenon, because wavelengths are not of similar dimension as a typical room. Standing waves can occur, which cause amplification of tones in particular places or cancellations in others. Therefore, the measured frequency response of a speaker under ideal circumstances in an anechoic chamber, as it should be measured, is not quite the same as what you hear in your room, because the room defines the real response in that range. Of course, there are other ways to achieve a response similar to one under ideal circumstances, even at home. ARTA, the software I use, for example, has the possibility to measure a gated response with a freely definable timing gate. In that way, you have the possibility to set your timing gate as big as to the first reflection on one of the surfaces of the room. In most cases, that's one between the floor and ceiling. If you position your speaker as centered as possible in your room, because it is the smallest distance. Usually that one is in the range of 300 to 400 Hz, I guess, but I'm not sure. Anyhow, somewhere in that range. To measure below that, you can measure in the near field, which has to be adjusted in volume to match the rest of the plot. What is a good frequency response? A good response should be balanced and linear, in my opinion. What does that mean? Balanced means that all ranges have roughly the same volume. That means that differences in volume should be as small as possible. Linear means that differences in volume between frequencies next to each other should be as small as possible. For example, a plot with many small peaks within a small range would be considered bad. Due to reflections and reverberation in mids and treble, a speaker in a normal room, for example at your preferred listening position, sounds different than under ideal circumstances, for example in an anechoic chamber. Why should you take the effort to create a linear and balanced response under ideal circumstances if you put it into an environment afterwards which isn't ideal and kind of destroys the response? Let's look at it from another angle. What outcome do you expect if the basis is crap? If it doesn't have an ideal response in an ideal environment, it won't become better inside a normal room. On the contrary, it will become worse. At least that's why you should put some effort into designing by trying to achieve a balanced and linear response. Why is that good? If all frequency ranges are transmitted at the same volume and no dips and peaks are present, then the sound is as neutral as possible. That is what hi-fi basically means. High fidelity, as original as possible. If all ranges are played with the same volume, it is most likely that it sounds nearly like the original. The reproduction sounds as natural as possible. There are of course other examples and preferences of people. Surely it's a matter of personal opinion, taste and fashion. In the 80s and 90s there was, for example, this trend, which in German had the nickname Bathtub Response. This meant an emphasis at bass and treble, that the plot looked like a cutaway drawing of the bathtub. Kirby Meets Audio called it smiley face response. That even made sense for certain music styles, as for example techno music. Their bass was important and treble to better be able to recognize rhythm, and vocals and melodies stood more in the background due to their repetitive nature. Therefore, it becomes clear that there were many speakers with bathtub response on the market. Another example I've read about in the German hi-fi magazine Stereo Play in the early 90s was about British speakers and even hi-fi components having an emphasis in the mids to be able to listen to melodies more clearly. This also improves speech comprehension because it is in the region where the most important information in speech is transmitted. I don't remember exactly, but I think the amplifier I mean had been manufactured by Name, N-A-I-M. It was not possible to switch off this emphasis, as far as I remember. If such a thing is good or bad is also a question of personal taste. I'd say the more balanced and linear the response is, the more universally you can use the speaker and the more music styles sound good when being played through it, because everything sounds as original as possible. Well, original of course is a vague term in combination with electronic music. Also the preference and taste of the sound engineer at mixing the recording plays a role. But that is something else. The other German DIY loudspeaker magazine Klang und Ton I read for several years called Non-Balanced Speakers with Character and said something like, you have to get used to the sound. Well, I'll put that under personal preference, which are not my own. It's one of the reasons I don't read that magazine any longer. Another thing which is correlated with balance and linearity is spatial representation. This has to do with psychoacoustics. If the response is balanced and linear, your brain, which knows certain sounds, as far as you experience those voices or instruments live and in reality, and it knows how they should sound and therefore it corrects mistakes. It does that all the time, for example at optical illusions. That's one reason why testimonies of eyewitnesses sometimes differ. The error correction capabilities of your brain are really huge, but it costs processing power of your brain to reconstruct the things you know. First thing it does is correction of frequency responses if it doesn't seem right. Then it has to reconstruct spatial representation from only 2 speakers, which is certainly a reduction of reality, because everything is transmitted through only 2 small spots. Therefore might be not enough processing power left to reconstruct the full spatial representation or certain details. This leads to suboptimal sound quality. Something else I want to mention is cutoff frequencies. I already explained what good cutoff frequencies are and mentioned 40 Hz and 40 kHz. 40 kHz is of course no must-have, because many dome tweeters only even reach 20 kHz due to technical reasons. The real question is how you count it. At which point does the frequency count, because there is normally no jump in the curve. It is usually continuous. Hobby HiFi say, and I agree, that the point counts at which the volume is reduced by 3 decibels. At that point, the reduction of volume is noticeable. It's also called F3. The German industrial standard for Hi-Fi says minus 10 dB, as far as I remember, which would be already half as loud. But manufacturers decide themselves which point they count, and often they don't tell you why or which. That German standard was outdated shortly after it was published in the late 1960s anyway. That happened because quality of hi-fi equipment, including speakers, rose so quickly that that standard was surpassed in the early 70s, so within a few years. Well, that is for home equipment. The standard also defines studio equipment, but I'm not an expert at that. So it is always good to know how a manufacturer counts. If there is no info about it, any given value is basically worthless. The value might be altered for marketing reasons. So if no circumstances are given, throw those values in the bin. On my notes it says that the German hi-fi standard defined that a maximum tolerance of plus minus 4 decibels is allowed for a speaker within 40 Hz to 16 kHz. For tape machines and amps, something else was of course relevant. The standard also said that distortion, a podcast about that will follow, distortion above 100 Hz at an SPL of 96 dB had to be 40 dB less, which is below 1%, which means that the absolute SPL of distortion must be below 56 dB then. Nowadays, distortion levels are significantly lower. For example, the beryllium domes by Scanspeak, SB Acoustics or CS, have extremely very low distortion. Due to their modern construction with a big surround, D2 is a bit higher than the rest, but D3, D5 and so on are so low that they nearly never surpass the lowest value that can be measured, which in Hobby HiFi I think is 0.01%, minus 100 decibels. That makes the standard even more insignificant now. That's all for today. Next planned topics are impedance response, crossover networks, distortion plot, waterfall spectrum, tele-small parameters, and various enclosure types. If you have other suggestions, please write a comment below. If you found a mistake, please have a look at the comments to see if I already corrected it. If I didn't, then leave a message. Thank you for listening, and I'm happy if you listen to my other podcasts or watch some of my videos. If you like what I do, please subscribe. Until next time, bye!